A special lecture on ML Type Inference. This is video number 3, consisting of exercise solutions with comment on vacuous truth and proof by induction. So I first review exercises I gave in the previous lecture and show some sample solutions. So I gave this exercise in the video lecture 2. Exercise 1, consisting of 2 questions. First is this one. Consider a proper definition of big intersection X when X is empty. In the previous lecture, this definition is restricted to non-empty X. So this question asks you to generalize the definition. This exercise only asks you to consider a proper definition, so any consideration would be fine. And I gave one possible answer, solution, which is this one. The strategy is to take the previous definition as is, right? So this definition for no-empty case is defined to be the set of all elements named A satisfying this condition. A is in Y for all Y such that Y is in X. And one strategy is to take this definition for empty set X. Then you get this set A where this condition is actually when X is empty, then this condition is true since there is no Y in X. So this is true. So you get this set for X is empty when X is empty. So A is condition true, no condition, right? So any A, right? So A is taken from the universal set. So this set is a set of all elements, the universal set. So this is one consistent definition of this definition, big intersection of the empty set. And so this is first question. And second question, the intention of this second question is to ask you to show that the property being closed under F is preserved by this big intersection operation. So let delta be a set of sets. Show that if each element of delta is closed under F, then so is this intersection. This is simple calculation. So your goal is to show that this delta is closed under, so this big intersection of delta is closed under F, using the assumption that each element of delta is closed under F. So in order to show, the conclusion we wanted to show is this one. So in order to show this, you pick arbitrary constructor F, and arbitrarily, so this F is element of F is a constructor function associated with arity n, and so according to this n, you pick arbitrary tuple, n tuple of this set, and show that applying this to this tuple belong to this intersection. Because this is the intersection, so sufficient condition is that this application, the element, this element belong to any set in delta. So you take an arbitrary element X in delta, right? Since the assumption of X is that assumption of X is closed under F, so you use this assumption that X is closed under F. Then this application is in the set X. Since X is taken to be any member of delta, you have done this this conclusion. So this implies that this intersection is closed under F. So this concludes the one possible solution to this exercise. Some comment on the solutions I gave, the example solutions I gave. First is about the consistent definition. I said, without any justification, that the definition this definition, big intersection of the empty set is a universal set. And I said that this is a possible consistent solution, right? But so natural question is, what do you mean by consistent definition? Well, by this consistent, I mean various expected equations still hold, expected solution or valid equations under the previous definition of big intersection still hold for the case of the intersection. So this comment is in the form of additional exercise, small exercise. So small exercise asks you the following. Show, for example, that this equation holds when A or B are empty. This equation, you can check that this equation holds for non-empty A and B, right? So you can see intuitively that the meaning of this, you can interpret it this way. So this is the intersection of this and this. So any element in this set is any element in both this and this one. And this is a big intersection. This is a big intersection. So this set is a set of such element that belong to any element of A and also any element of B. That is the same meaning as this one. So this is the intuitive justification. You can calculate this in non-empty case. So this small exercise asks you to show this for A or B are empty. Well, the proof is simple, right? Almost trivial. So by symmetry, it is sufficient to consider the case of A only. B is exactly the same. Not exactly, but B is essentially the same. So you substitute A to be the empty set, and you get this one. And so this, by applying the definition just to be defined that this is a universal set, so this is by definition equal to this one, but universal set intersects with any yield this part, so you get this part. And now this B is obviously same as union of empty set. So this is the right hand side. So this and this are equal. So this concludes the proof, simple proof of this simple question. The second comment on this possible solution I gave is also formulated in the form of exercise. So I stated that this condition, this is the original condition on the intersection, big intersection of set of sets. And I said that since y, there is no y in x, so this condition is true. And comment is formulated as another exercise that asks you to verify this. This condition is true when x is empty. In this case, there is no calculation needed, but this is trivially true, by the principle of logical reasoning. The proof is simply this. There is no y such that y is in x. So the universal property, this is a universal proposition. The universal proposition is vacuously true. So this is the end of this proof. So simply this. Actually, the rationale of making the comment, the second comment, is to explain the notion of vacuous truth. The logical reasoning I presented, that is, any universal proposition on the empty set is true vacuously. So the notion of vacuous truth, this could be an obstacle in understanding logical reasoning with false or a predicate on the empty set. So example of vacuous truth, very typical example of vacuous truth is implication with false antecedent. Antecedent is the assumption part of the sentence, implication sentence, right? So If P is false, then if P is n cube, this proposition is always true. Always here means true for any q, right? So this proposition is therefore trivially or vacuously true when P is false. The validity of this sentence is based on the logical principle, trivial logical principle. However, this notion, vacuous truth, may be an obstacle in understanding logical reasoning is false or predicates on empty set. I believe reason of this difficulty or maybe oddness of this logical principle comes from the differences between the defined semantics of logical connectives and usual meaning of natural language conjunctions of this if then else or for or something. And due to this fact, I think it is difficult to explain this vacuous truth in English or in natural language. So instead of trying to explain why this vacuous truth is valid, I only show some famous story, introduce some famous story on this vacuous truth. The story is known as Bertrand Russell is the Pope. So if you search on the internet with this sentence, you will find some multiple pages describing this story with differences. So there are several versions. And this story is known to be due to Russell, Bertrand Russell, so Russell's anecdote. And I don't know exact citation or exact origin or exact literature describing this story. So this is based on my searching the internet. So one version of the story goes as follows. At a dinner table or lecture or seminar, two persons, one is Bertrand Russell and the other is a guest I call R and G. These two had the following conversation. R, Russell said, anything can be proved from a false proposition. And then guest challenged, well, then prove that you are the Pope from 2 = 1. Then Russell replied, well, easy, and showed the following proof. I and the Pope are two persons, but 2 = 1, so I and the Pope are one person. Therefore, I am the Pope. And the guest has some silence, right? So this is a famous and quite enjoyable story symbolizing the usual understanding of language and logical reasoning, some gap between logical reasoning and usual sense of validity. So allow me to continue a little bit more about this digression on vacuous truth. So supplement on vacuous truth. So vacuous truth originally, in our case, is a universal proposition on the empty set, right? So this is another example of vacuous truth. So if X is empty, then for any Y such that Y is in X, P of Y is always true, where P is some predicate. Here always means for any predicate P. This sentence is true, and this sentence is a universal proposition for any or for all, the same thing. For all Y such that Y is in X, P of Y, right? So this proposition. This is always true, and this is another example of vacuous truth. So there is no nice joke story I can find on the internet, so I improvised one. So this story is I said that the Bertrand Russell is the Pope. I can't find any citation, but this joke you can cite if you please. So this story, paying attribute to Bertrand Russell, is a Pope. The situation is the following: a rebuttal session on a conference. There are two persons, A, poor author, R, great reviewer. I note that this is a joke. So they do not represent any particular conference, author or reviewer, right? So let's continue. Let's go back to this situation. A rebuttal session. Author claimed the following: any universal proposition can be proved on the elements of the empty set. Then reviewer challenged, well, then for empty X, prove that for any element Y of X, Y is the Pope. If you can't prove this, your paper is a reject. Then author replied, obvious, but if you so desire, and gave this proof. So proof goes, let Y be any element such that Y is in X. Since X is the empty set, X is equal to the empty set, and empty set is a subset of any set. So pick this set, singleton set containing the Pope. Then since Y is in X and X is a subset of this set, therefore Y is in this set. However, this is the singleton set, so Y is the element of this singleton set means Y is the Pope. Gave this proof, and reviewer, after some silence, said, but still your paper is a reject. I note that this is a joke, so they do not represent any particular conference, author or reviewer. So I hope you enjoyed this joke. Now turn to the main topic of inductive closure. We have been studying inductive closure. So this slide summarizes so far we have studied. So in computer science, various data structures in general, data structure in the general sense, including languages and language components such as expressions, types, or programs, proofs, various documents such as JSON, or data structure of a program, lists or binary trees, all are regarded as inductive closures. So we studied two characterization of inductive closure, which is denoted by this one, int C, F, right? And two characterizations. One is this one, intersection of all the sets containing C and closed under F. Another one is a set of union of X sub I starting X0, which is C, and making Xi plus 1 as a union of Xi and F of Xi. These two characterizations, so we have studied. The main new technical contents of this video 3 is proof by induction and induction principle. We learned these in the following 5 steps. I first review proofs and proof by induction, and then give a simple example proof, and from this simple proof we extract the generic pattern of inductive proof, and then provide two mathematical rigorous understanding of proof by induction. First is based on this property, this property, inductive closure as a generation of a set of element or a big union of a sequence of sets. And the other one, which is actually the basis of inductive proof, which is called induction principle. This is based on the defining property, defining equation of this inductive closure. So the following the policy of the lecture, so my policy explaining the essence clearly and rigorously, we go through the details of these steps. So this is a note that if you are already familiar with inductive proof, you may skip 1 through 4 and just review 5. And if you want to know inductive proof method only without their mathematical details, mathematical basis, you may skip 4 or 5 and go through 1 through 3. In particular, this proof pattern, which should be useful in the rest of this lecture and also in any formal reasoning about various properties of languages. Review of proof by induction. Right? Actually, there are a number of proof methods, such as proof by contradiction, application of famous theorem, and proof is just a corollary of a theorem, and so on. Or proof is just easy or obvious or well known. Now, these are reserved for great mathematicians. Now, for us to prove various language properties, such as typing and so on, induction on inductive closures, this is almost the only method. So mastering this method is an important step in programming languages. So I make some comment. So it is actually straightforward to master inductive proof, whose structure is determined by this very definition of inductive closure. But this fact, it is straightforward to master inductive proof, doesn't mean that proving some property is easy or straightforward. Now, the important art of proving properties lie in finding out right propositions. So if you want to prove something, some desired property, and write down the property, but it is not easy to prove by induction. So often you get stuck in induction step. So usual strategy to get out of this difficult situation is to try to generalize the proposition to prove. It's a very general strategy, and there is no systematic method to show interesting property of a set of languages. So this is the reality. And this situation is analogous to program coding, program construction. I wanted to introduce or show this part in some other occasion, probably some other lecture. So proof example, let's look at a very simple proof example using this set of lambda terms as a target. Right? And so you now know that this notation is a BNF denoting the set generated by these 4 components, or closed under, including this and closed under this and this construction. Right? And for this lambda term, let's consider this very simple proportion. E, element of lambda term, has an equal number of left and right parentheses. Now, this proposition is obvious, right? So left and right parentheses are introduced at the same time for this term constructor or this term constructor. So this is obvious, but formal proof, you use induction. So this is a proof of this proposition. So in order to prove this, we introduce notation LPOB and RPOB to be the numbers of left and right parentheses in E, and then do the following. First, you state this, we prove this proposition LPOB equal RPOB by induction on the structure of E. And then you do case analysis corresponding to these 4 components. So for first case, E equals X, you show directly LP of X equals 0 equal RP of X, so you are done. Same as this constant, right? LP of constant equals 0, which is equal to RP of constant. And then case for this component, lambda term, containing this E inside. For this, you say the following by the induction hypothesis and write down the proposition you are proving, that is this one, for this component E1, that is LP of E1 equal RP of E1. And using this assumption, you show the desired property, which is this and this is equal, and you calculate this. So according to the meaning of LP of this lambda term, which is 1 because you have one parenthesis here, and then any other one comes from this E1, so 1 plus LP of E1. Same as right parentheses, so that right parenthesis E1 plus 1. 1 is here, you have this parenthesis, and so under the assumption this and this is equal, this 1 plus LP of E1 and 1 plus RP of E1 is equal, so you are done. Similarly, for this component, you have two occurrences of this lambda term E1 and E2. For these two, you have two induction hypotheses. So proof goes by the induction hypotheses, and you write down two induction hypotheses, this one and this one. And using these two hypotheses, you show that this and this are equal by just simple calculation. So this is a structure of proof, and it's a concrete example proof. And this, from this, you saw the clear structure of inductive proof. So we can extract the proof pattern from the previous simple proof. So this is a proof pattern of inductive proof on this inductive closure. So proposition, I abstractly write some proposition, typical proposition. So proposition looks like this. The property P holds for the set, and this set is the inductive closure generated by this constant and the constructor. And for the proof, you have the proof of this shape. So this is a proof template. So first you pick arbitrary element from this set, from this inductive closure, and then say the following: proof is by induction on the structure of X, and do case analysis for this constant. For each constant, you do case analysis. For example, if case X is equal to Ci, then using the property of Ci, you directly show P of Ci, and you exhaust all cases for all Ci in this given set, in these constant. And then next group of cases are for this constructor applied to tuple. So case X equals this Fi of RTNI applied to this tuple consisting Ni of this inductive closure element. In this case, you say the following: by induction hypothesis, P of Xi through P of Xni are true. These property hold. Then using this assumption, and possibly with additional property of this constructor, you show this property. And you exhaust the cases for all constructor in F, in this. So this is a proof. Then you completed the proof. The proof is, so if you find out, if you write down this proposition P to be proved, and this cases without the actual body, then proof is halfway done. So the all remaining thing is to complete each of this body, right? So this is a generic pattern of inductive proof. The inductive proof always look like this shape. One reason that we have gone through various details of inductive closure and proof by induction is to get the rigorous understanding of defining some language or types or some set and doing proof, rigorous proof by induction. So this slide shows one mathematical understanding of inductive proof. For this understanding, we take the mathematical property of this one. Inductive closure is defined by the sequence of set and take a union of everything. In this understanding of the inductive closure, we understand that the inductive proof shows these two. First, so but the basis P of Ci for each Ci in C. This property establishes that the desired property P on set x0, right? And then induction step, that is showing this component, showing P for the component constructed by Fi using the induction hypothesis P of xi, establishes P on xi plus 1 by assuming P on xi. So, inductive proof on P on inductive closure is regarded as a proof on P on each xi by mathematical induction on I. This is one mathematical understanding of inductive proof. The previous understanding of proof by induction as a mathematical induction on the sequence of sets, that is good enough and intuitive and rigorous. However, there is another characterization which is in some sense more direct and more basic. That is the induction principle. So this is usually taken as a mathematical basis of proof by induction. So let's go over this. For this purpose, we consider the defining equation, this one, of inductive closure, right? So this is now, we have seen this a number of times. So inductive closure is the smallest set of this set of all sets containing C and closed under F. From this defining equation, we have the following characterization. Proposition, usually called the induction principle of inductive closure. This property, if a set P contains C and closed under F, then this inductive closure is a subset of P. And those who followed so far immediately see that this property is trivial. I mean, by definition, immediately follow from this very definition, right? No question about it. And this trivial property is indeed the basis of proof by induction. So to understand this, let's consider this set P, which is the set of all element x, such that P of x is true. Right? Then proof by induction shows following two. Proof by induction shows consists of two parts. One is the basis, so that for each Ci of large C, you show this P of Ci is true. And this base case simply establishes that this C, large C, is a subset of P, because P is a set of all element x, such that P of x is true. So if you show that P of Ci is true, then C is a subset of P. And proof by induction consists, another component of proof by induction is the induction step, which will show this P of this element is true under the assumption that P of x1, this should be 1, P of x1 through P of xn is true. Under this assumption, you show P of f applied to this tuple is true. This is nothing but showing that P is closed under F, right? So namely the proof by induction. The proof shows that P contains C and closed under F. So this is what is going on by proof by induction. And so by this trivial property, if you completed proof by induction, then property P holds for all elements of the set. So this is a rigorous understanding of proof by induction. So this is the end of this lecture number 3.